Hello everyone. So welcome to my second lecture on multiple integrals. So in last lecture we talked about double integration. Okay, so I gave you the idea on how to find double integration, or you can say what is the importance of double integration with the help of single integration, GeoGebra, and using the rainfall example. Now question is how to solve or how to find volume under the surface. Okay, so one way is to go by the Riemann sum method. And today I'm going to take two examples. First one will be a very specific example and the second one will be a general example. And once we will see those two examples, we will see that it becomes quite complicated to solve an example using Riemann sum. But still it is important because whenever you want to approximate the integral, Riemann sum is the only choice. So one should know how to solve problems using Riemann sum. In next lecture we will see how iterated or iterated integrals help us to solve double, triple and so on integrations. But okay, that's the second part, and you will realize it's important when you will see that this is quite difficult to solve. Okay, so directly jumping towards the iterated integrals, let me tell you two examples on how to solve double integration using Riemann sums. Okay, and many times professor do ask you such kind of questions just to check your ability whether you have understood Riemann sums or not. Okay, so without wasting any time, let me take the first example. I am taking a very nice examples, very simple example, so that my calculations becomes easy. Okay, let me take the black marker. So suppose if my function is f of xy equal to x plus y, and suppose my domain, let me take my domain as, my domain is a rectangle, so my 0 less equal x less equal 4, 0 less equal y less equal 4. Okay, and the question, what is the question? Your job is you need to find a lower Riemann sum, you need to find upper Riemann sum. Okay, and you divide your region into equal subintervals, divide your D into equal subrectangles such that divide into, let me say, 4 equal subrectangles. Okay, so this is what the question is. Now you need to find the lower and the upper sum. Okay, now what is my rectangle over here? So let me draw my rectangle over here. So it is in the first quadrant, 0 to 4 and 0 to 4. Okay, so this is the rectangle over here. This is my region D. Now how many rectangles I want? Into 4 equal means, okay, right? So here it should be what? Here it is 2, here it is 2. Okay, what is this point? 4 comma 4 and so on. This is 4 comma 2, this is 2 comma 2, 2 comma 4. Okay, good. What is the first thing you do? To find the upper sum, you consider this rectangle. Let me call this as A1, A2, A3 and A4. Okay, let's first deal with LPF. So you look for the point where function is taking the minimum value in the rectangle A1. Now see, you have a very nice function x plus y. So you have to simply add up the components. So among these points, at which point function will take the minimum value? At 0, 0, right? Because at other points, you take any other point over here, those will be non-zero xy component. So minimum value will be at 0, 0. So what is f of 0, 0? It is nothing but 0 plus 0, which is nothing but 0. Now go to the second rectangle. At which point function will take the minimum value? So obviously it will be 2 comma 0, right? Because as you go away from this, you get increasing value of x and y, and indirectly your x plus y will be more. So at 2 comma 0, function is taking the minimum value. So you look f of 2 comma 0, which is 2 plus 0, which is 2. Now you go for A3. At A3 you look for the point where function is taking the minimum value. Again it will be the bottom left corner. So bottom left corner is nothing but 2 comma 2. So f of 2 comma 2, which is nothing but 2 plus 2, which is equal to 4. And now you go for the fourth rectangle, and again at the bottom left corner function will take the minimum value, which is nothing but 0 comma 2, which is 0 plus 2 equal to 2. So we took the points where function was taking the minimum value and we evaluated your function at those points. Good. Now what does the Riemann theory says? You multiply the height with the area of the rectangle. Now what are the areas of rectangles? All of them are having the side 2 into 2. So area of all the rectangles. What is the area? area of all ai's, I can be 1 2 3 4, it is nothing but 2 into 2, which is nothing but 4. Fine. Now what do you do? What is the approximated volume? Your approximated volume is nothing but minimum value into area, right? Area of the rectangle into the minimum value will give you the cuboid, if you remember my last lecture. So here in this case it will be nothing but 0 into area plus, you go for the second rectangle, 2 into area plus 4 into area plus 2 into area. You can take out 4, which is the area which is common, and you simply add them up. What you get? 4 5 6 7 8, so 32. So this is called as, this is the lower sum for the given rectangle or given function over the given rectangle. So this is how you find the lower Riemann sum. Well, in this case, lower Riemann sum, to find the lower Riemann sum, we computed the value of the function at the lower left corner. Okay, lower left corner, this were the points we used. Because the function was x plus y, so that's why it was easy to calculate at the low. We know that at lower rectangles or the lower left point, my minimum value will occur. But when you have a complex functions, it becomes difficult at which point function will take the minimum value. Suppose if I give you 10 raised to 7 minus tan inverse of x plus y plus e raised to xy, then it becomes difficult to tell at which point function will take the minimum value. Okay, that's why iterated integrals are much more good to play with. But anyways, so I hope you understood how to find the lower Riemann sum, which is 32 in this case. Now if you want to find the upper Riemann sum, what will you do? You will look at for each of the rectangle, you will look at the top right corner, this point, this point, this point and this point. Again, because my function is x plus y, my maximum value will come whenever we are moving away from x and y, right? So to calculate the upper sum, UPF, okay, so let me erase this part. Again, the area will be same, so not a problem. The only thing is what will be the upper sum, so you need to find value of the function at which point you will find, that is the question. So here for the first rectangle, at 2 comma 2 function will take the maximum value. So what is f of 2 comma 2? It is 2 plus 2, which is 4. And for a2, at which point? At 4 comma 2 function will take the maximum value, so it will be 4 plus 2, which is 6. For a3 it will be 4 comma 4, which is 8, and for a4 it will be 2 comma 4, which is nothing but 6. So now what will be the approximated volume? 4 into area of rectangle, 6 into area of a2, 8 into area of a3 plus 6 into area of a4. So area is 4, common for all the sub rectangles. I have to simply add 4 plus 6 plus 8 plus 6, 10, 10 plus 8, 18, 18 plus 6, 24, 24 4s are 96. So this is the maximum value your integral can take. Okay, so this is the upper Riemann sum. And we saw in our last lecture that your integral, double integration d, f of x comma y dA will always lie between upper Riemann sum and lower Riemann sum. I think it was 32, I think. So whatever your answer will be, it will always be between 32 and 96. Okay. In my next lecture, when I will tell you the idea of iterated integrals, you use that method to find the double integration of this, and you will observe that it has to be between these two numbers. Okay, so that was one thing. Sometimes they also tell you that like suppose it is difficult to visualize at which point you will have upper sum and lower sum. So what they will do is, your professor will tell you to find the approximated value of the volume using, you take the sample points as the midpoints. You take midpoints as the sample points and you find the approximated volume. So in this case, what will be the midpoint? Here it is 1 1, so 1 comma 1. Here it will be 3 comma 1. Here it will be 3 comma 3, and here it will be 1 comma 3. So instead of telling you to find upper and lower sum, they will say, okay, find the Riemann sum by taking sample points as the midpoints. So you have to take the midpoint and then you have to find the Riemann sum. So that is the first homework for you. You tell me what is the Riemann sum when you take midpoint as the sample points. Okay, so that's a very easy homework. You can easily do it. So you can pause the video and you can tell me the answer. Okay, now let's go for another example where if you have a partition in general where n will be involved. So let's see how to solve that example. Okay, so now let's go for the second example. Now here the function is f of xy equal to x into y. Again I'm taking the rectangle, but now I'm taking a smaller value, unit square I'm taking 0 to 1, 0 to 1. Okay, and now I have to find the Riemann sum, and then I have to find the value of double integration. So what is double integration? It is the limiting case of the upper Riemann sum or the lower Riemann sum. Okay, that is one thing. Now question is how to divide your segment, this segment and this segment into sub-rectangles, into sub-intervals, so that you get the sub-rectangles. That is the first question. Now see, whenever you have a continuous function, there is a theorem that whenever you have a continuous function, it's a Riemann integration, or you can say integration of that function always exists. So now here, since the function is continuous, therefore its double integration will exist. Okay, good. Now since the integration exists, there is a theorem. You take any Riemann sum, you take lower sum, upper sum, or you take the Riemann sum with the help of the midpoints, or you take any random point in that sub-rectangle, and then you find the Riemann sum, and then you take the limit n going to infinity. You always get the same answer. So therefore, whenever the function is integrable, the limit of lower sum, limit of upper sum, limit of any arbitrary sum will always converge towards the same number. Okay, so because of this nice theorem, what we will do is we will take the very nice partition, because I know that for any partition and for any points, good things will happen. Everything will converge to the same number. So because of that thing, what we will do is we will take very nice partition of this rectangle. So what you do is you divide this into equal sub-intervals. Okay, so what you do, this is 0, you take this as 1 by n, 2 by n, 3 by n, up to so on 4 by n, up to this is n by n, and same thing over here, 1 by n, 2 by n, 3 by n, if you keep on going, this is n by n. So what rectangles you get? For 1 by n, you draw these vertical lines over here. For here 1 by n, it will be horizontal lines, and so on. So these are the rectangles you have. These are the rectangles you have. Now how many rectangles are there? Here there are n, here there are n intervals, so therefore you have n square sub-rectangles. Okay, that is the first thing to observe. You have n square sub-rectangles. So this will be a bit complicated, but I'll be going a bit slow. You can adjust the speed of the video, okay, as per the YouTube settings. But okay, let me go a bit slowly. So you have n square sub-rectangles. What is this? Is 1 by n, this is 1 by n. So what is the area of this sub-rectangle? 1 by n into 1 by n, which is 1 by n square. What is area of this sub-rectangle? This length is again 1 by n, 2 by n minus 1 by n. So this is 1 by n, this is 1 by n. So this area is also 1 by n square. In general, you take area of any. So let me denote this by a1 comma 1. This is a1 comma 2, a1 comma 3 up to a1 comma n. Now let me call this a2 comma 1, a2 comma 2 up to a2 comma n. So this will be a n comma n. So you have total n square subrectangles. So area of each aij is nothing but 1 upon n square. This is the area of each subrectangle. Okay, good. So we got the area. Now what is the next thing? I want to find the upper sum or lower sum or any sum. So what you do is you take any point in this subrectangle. So for simplicity, let's take the topmost right corner. Let's take the topmost right corner for each of the subrectangle. You have to choose any point. You can also do with bottommost left corner, but that I will give you as a homework question. So let me take this as a topmost left corner. Okay, now what I will do, I will concentrate in this interval, in this subrectangle. So for f of which point I will take? Topmost. What is topmost point? It is nothing but 1 by n comma 1 by n. So this is nothing but 1 by n square, because function is what? You have to simply take the product. Go to the second rectangle, a1 comma 2. What is the point? F of 2 by n comma 1 by n. So what is this? 2 by n square. What is f of next rectangle? 3 by n comma 1 by n, which is nothing but 3 by n square. And if you keep on going, f of n by n comma 1 by n, which is nothing but n by n square. So this is the value of the functions for the bottommost lines sequence of rectangles. Now you go for the second sequence of rectangles. Now for this a21, what will be the point? F of 1 by n comma 2 by n, which is nothing but again 2 by n square. Then f of, what is the next point? 2 by n comma 2 by n, which is nothing but 4 by n square. Then the next point is 3 by n comma 2 by n. Here 2 by n will be fixed. So this is nothing but 6 by n square, and up to so on f of n by n comma 3 by n. So this is nothing but n by 3n by n square. So this is the value of the function at the topmost right corner point for the second sequence of rectangles. So here it was 1, 2, 3 in the numerator. Here it was 2, 4, 6. It's a multiple of 2, sorry. Now when you go for the next one, this will be what? 1 by n, 3 by n. Okay. So for the third set of rectangles, you will get 3 by n square, 6 by n square, up to 3n by n square. This is the value of the function for the third series of rectangles. Similarly, for the last one, you will have the multiple of n. So let me erase this. So if I erase this part, okay, so now let me erase this also. I hope this rectangle is in your mind. If not, you can draw this in a pen and paper and then you can refer. So what is the volume, or what you can say the Riemann sum? Riemann sum for the function for the given partition, or for the given partition for the given function. Both the notations are same, doesn't make a difference. This is equal to, what is the Riemann sum? Value of the function into area of rectangle. Now all the rectangles is having the area 1 by n square. So let me take out that 1 by n square common, because all the sub-rectangles is having the same area. Now what you do, you add up all the functional values, right? Value of the function into area, plus value of the function into area, plus value of the function into area. So I'm taking out area outside 1 by n square. Now you have to simply add. So the bottommost rectangle will have the value 1 by n square, plus 2 by n square, plus 3 by n square, plus dot 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 n by n square. Okay, this was for the bottommost rectangle. Plus now you go for the second one. So what is that? That is nothing but 2 by n square, plus 4 by n square, plus 6 by n square, plus 2n by n square. Then you go for the third series of rectangles, 3 by n square, plus 6 by n square, plus 9 by n square, plus 3n by n square, and so on. If you go for the topmost rectangle, it was n upon n square, plus 2n upon n square, plus 3n upon n square, plus n into n upon n square. This will be the value of the functions for the topmost sequence of rectangles. If you have any doubt in any of these steps, make sure you can ask in the comment section. Okay, and hold this multiplied by the area, which is 1 upon n square. Okay, good. Now 1 upon n square again. There in the denominator n square is common. What is the numerator? 1 plus 2 plus 3 plus n. What is the sum of first n natural numbers? N into n plus 1 by 2. So that is my first value. Go to the second one. You can observe whole divided by n square. You can take out 2 common. What is left? 1 plus 2 plus 3 plus n. Again, what is sum of first n natural numbers? N into n plus 1 by 2. Plus, go to the third series. Again, divided by n square. You can take out 3 common from each of the term. What is left? 1, 2, 3 up to n. Again, what is sum of first n natural numbers? N into n plus 1 by 2 plus dot dot dot. Again the same thing over here. You can take out n square is the denominator common. You take out n from the numerator. What is left? 1. It is 1. 1, 2, 3. What is sum of first n natural numbers? N into n plus 1 by 2. Fine. Okay, good. Now here if you observe, you have 1 upon, you can take out n square outside here also. So it is n raised to 4. From the numerator, you can observe n into n plus 1 by 2 is common. So you can take out n into n plus 1 by 2 also common. Now what is left? Here nothing is left. So 1. What is left here? 2. What is left here? 3. Plus dot 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 n. And 1 by n raised to 4 into n plus 1 by 2. What is this? Sum of again first n natural number, which is again n into n plus 1 by 2. So if I take out n from here outside, if I take out n from here outside, n square, n4 will go away. 1 plus 1 by n, 1 plus 1 by n whole divided by 4. Oof, that was long. So finally we got the Riemann sum as 1 plus 1 by n into 1 plus 1 by n by 4. Okay, if you want you can take this as a square also, not a problem. This is whole square. Now once you have the Riemann sum, how do you find double integration? You simply take the limit of that Riemann sum. So if I take the limit, so my volume, which is nothing but double integration over d xy dA, my function is what? Xy. It is limit n going to infinity Riemann sum for the partition for the function. Either you write fp or pf, doesn't make a difference. Limit n going to infinity. What is this? 1 plus 1 by n whole square upon 4. As n goes to infinity, this is nothing but 1 by 4. So volume of the surface below f of xy equal to xy and above the rectangle, that volume is 1 by 4 units. Well, you can also, my suggestion is you try to visualize the graph of this function. I told you how to use GeoGebra in my playlist on function of several variables. I will put the link in the description. You can have a look. So finally the answer is 1 by 4. Now we will see in the next lecture using iterated integrals. This will hardly come in 3 lines or 4 lines. But then again, one should, to understand the definition of double integration, you should know that how to solve the problem using Riemann sums. And this will help you when you will study with approximations. Right now when you do your engineering, it won't help you that much. But trust me, when you go for higher studies, when you play with approximations, this will really help you. So I hope you understood today's lecture. If yes, do not forget to like, share and subscribe. Thank you.